Hello and welcome. In this video, we'll be exploring a fundamental concept in differential equations: separable differential equations. By the end of this session, you will be able to identify, solve, and apply separable differential equations to real-world problems, which is a key skill in the IB analysis and approaches higher-level curriculum. Let's begin by defining what a separable differential equation is. A differential equation is called separable if it can be written in the form dx equals f of x times g of y. This means the rate of change of y with respect to x can be expressed as a product of a function of x only and a function of y only. Let's look at a few examples to make this clear. Consider dx equals x times y squared. Here, f of x is x and g of y is y squared. Since it's a product of a function of x and a function of y, it's separable. Next, dx equals y squared plus 3. This might not look like a product at first, but we can write it as 1 times the quantity y squared plus 3. So f of x is 1, and g of y is y squared plus 3. This is also separable. Finally, dx equals the quantity x plus 2, all over y cubed. We can rewrite this as the quantity x plus 2 times 1 over y cubed. So f of x is x plus 2, and g of y is 1 over y cubed. This is also a separable equation. The key idea is that we can separate the variables. This means we can rearrange the equation so that all terms involving y are on one side, and all terms involving x are on the other. Starting with our general form, dx equals f of x times g of y, we can divide both sides by g of y. This gives us 1 over g of y times dx equals f of. Notice that the left side now only contains y and die, while the right side only contains x. Now that the variables are separated, we can integrate both sides with respect to x. We integrate the left side, 1 over g of y times dx, and the right side, f of x. The integral of f of x with respect to x is straightforward. For the left side, we can use a substitution. Let u equal y. Then do equals dx. This is a direct application of the chain rule in reverse. So the integral of 1 over g of y times dx becomes the integral of 1 over g of y di. This is a crucial step. It allows us to integrate the y terms with respect to y. This leads to our general method for solving separable differential equations. Integrate 1 over g of y with respect to y, and integrate f of x with respect to x. The result will be an equation relating y and x. Let's recap. We've learned to identify separable equations and the general method for solving them by separating variables and integrating. Now, let's put this into practice with some examples. In this scene, our objective is to solve a general separable differential equation and express the solution in a clear standard form. Let's solve the differential equation dx equals x times y. This is separable with f of x equals x and g of y equals y. First, we separate the variables. We divide by y and multiply by dx. This gives us 1 over yd equals x dx. All the y terms are on the left and all the x terms are on the right. Next, we integrate both sides. We set up the integrals. The integral of 1 over y di equals the integral of x dx. Now we evaluate the integrals. The integral of 1 over y is the natural logarithm of the absolute value of y. The integral of x is 1/2 x squared. We add a single constant of integration, c, to one side. This is the general solution in implicit form. To get the explicit solution for y, we need to solve for y. We do this by exponentiating both sides. We raise e to the power of both sides. On the left, e to the power of yin simplifies to y. On the right, we have e to the power of 1/2 x squared plus c. Using the rules of exponents, we can split the right side. E to the power of 1/2 x squared plus c is the same as e to the power of 1/2 x squared times e to the power of c. Now let's consider the constant e to the power of c. Since c is an arbitrary constant, e to the power of c is also an arbitrary positive constant. We can call it a. So we have y today equals a times e to the power of 1/2 x squared, where a is a positive constant. To remove the absolute value, we introduce a plus or minus sign. This gives us y equals plus or minus a times e to the power of 1/2 x squared. We can simplify this further. Since a is an arbitrary positive constant, plus or minus a is an arbitrary non-zero constant. Let's call this new constant b. So the general solution is y equals b times e to the power of 1/2 x squared, where b is any non-zero constant. It's important to note that this solution does not include the case y equals 0, which is a valid solution to the original differential equation. We can include it by allowing b to be 0. To recap, we successfully solved a separable differential equation by separating variables, integrating, and then solving for y to get the explicit general solution. This process is a cornerstone of solving these types of equations. Our objective in this scene is to solve another separable differential equation, this time involving a polynomial function of y. Let's solve the differential equation dx equals 1 over y squared. This is separable, with f of x equals 1 and g of y equals 1 over y squared. First, we separate the variables. We multiply both sides by y squared and by dx. This gives us y squared di equals dx. The variables are now separated. Next, we integrate both sides. We set up the integrals. The integral of y squared di equals the integral of dx. Now we evaluate the integrals. Using the power rule for integration, the integral of y squared is y cubed over 3. The integral of dx is x. We add a constant of integration, c. This is the general solution in implicit form. To get the explicit solution for y, we need to solve for y. First, we multiply both sides by 3. This gives us y cubed equals 3x plus 3c. Since c is an arbitrary constant, 3c is also an arbitrary constant. We can just call it c again to simplify the notation. So we have y cubed equals 3x plus c. Finally, to solve for y, we take the cube root of both sides. The explicit general solution is y equals the cube root of the quantity 3x plus c. In this scene, we successfully solved a separable differential equation with a polynomial term. We followed the same steps: separate, integrate, and solve for y. This demonstrates the versatility of the method. In this scene, we'll tackle a more complex separable differential equation and introduce the concept of a particular solution. Our objective is to solve the differential equation dx equals e to the power of 2i times cos of 3x, given the initial condition that y of 0 equals 0. First, we separate the variables. We divide by e to the power of 2i and multiply by dx. This gives us 1 over e to the power of 2i equals cos of 3x dx. We can rewrite the left side as e to the power of negative 2y dy. Next, we integrate both sides. We set up the integrals. The integral of e to the power of negative 2y di equals the integral of cos of 3x dx. Now we evaluate the integrals. For the left side, we use a u substitution with u equals negative 2e's. For the right side, we use a u substitution with u equals 3x. The integral of e to the power of negative 2y is negative 1/2 e to the power of negative 2y. The integral of cos of 3x is 1/3 sin of 3x. We add a constant of integration, c. This is the general solution. Now we use the initial condition y of 0 equals 0 to find the specific value of c. This will give us the particular solution. We substitute x equals 0 and y equals 0 into our general solution. E to the power of 0 is 1, and sin of 0 is 0. So the equation simplifies to negative 1/2 equals c. Now that we have the value of c, we substitute it back into the general solution to find the particular solution. The particular solution is negative 1/2 e to the power of negative 2i equals 1/3 sin of 3x minus 1/2. We can solve for y to get the explicit form. First, multiply by negative 2. This gives e to the power of negative 2y equals negative 2/3 sin of 3x plus 1. Next, take the natural logarithm of both sides. This gives negative 2y equals the natural log of the quantity negative 2/3 sin of 3x plus 1. Finally, divide by negative 2. The explicit particular solution is y equals negative 1/2 times the natural log of the quantity negative 2/3 sin of 3x plus 1. To summarize, we've seen how to find a particular solution by using an initial condition to determine the constant of integration. This is a common requirement in IB problems. In this scene, we'll explore a common application of separable differential equations, modeling exponential growth and decay. Our objective is to solve a differential equation of the form dp dt equals kp, which describes exponential change, and use it to solve a real-world problem. Let's consider a problem. A salmon farm has an initial population of 80. The population grows according to the differential equation dpt dt equals 1/5 p, where t is time in years. We need to find an expression for the population p in terms of t, and then find the population after 10 years. The differential equation dp dt equals 1/5 p is separable. We can write it as dp dt equals 1/5 times p. Separating the variables, we get 1 over p dp equals 1/5 d. Now we integrate both sides. The integral of 1 over p dp is the natural log of the absolute value of p. The integral of 1/5 dt is 1/5 t. We add a constant c. Since population p must be positive, we can drop the absolute value. Solving for p, we get p equals e to the power of 1/5 t plus c. Using the rules of exponents, this becomes p equals e to the power of c times e to the power of 1/5 t. We can replace e to the power of c with a new constant, a. This is the general solution for exponential growth. Now we use the initial condition, p of 0 equals 80, to find a. Substituting t equals 0 and p equals 80, we get 80 equals a times e to the power of 0, which is 1, so a equals 80. The particular solution for the salmon population is p of t equals 80 times e to the power of 1/5 t. This equation allows us to find the population at any time t. Finally, let's find the population after 10 years. We substitute t equals 10 into our equation. P of 10 equals 80 times e to the power of 10 over 5, which is 80 times e squared. Using a calculator, this is approximately 591. So, after 10 years, the salmon population will be approximately 591. We have successfully modeled and solved a real-world problem using a separable differential equation. In this scene, we'll tackle a more complex application problem involving a cylindrical tank. This problem requires careful setup and the use of the chain rule. Our objective is to solve a related rates problem by setting up and solving a separable differential equation. Here's the problem. Water flows out of a tap at the bottom of a large cylindrical tank with base radius 2 meters. The rate at which the water flows is proportional to the square root of the depth of the water, h. Initially, the tank is full to a depth of 9 meters. After 15 minutes, the water is 4 meters deep. How long will it take for the tank to empty? Let's break this down. We are given that the rate of change of volume, dV dt, is proportional to the square root of the depth, h. This means dV dt equals k times the square root of h, where k is a constant. The problem involves both volume 5 and depth h. We need a differential equation that relates h and t. We can use the chain rule, dV dt equals dV dh times dh d. First, let's find dV dh. The volume of a cylinder is v equals pi r squared h. Since the radius r is 2 meters, v equals 4 pi h. Differentiating with respect to h, we get dV dh equals 4 pi. Now we substitute this back into the chain rule equation. We have dBt equals 4 pi times d. We also know dT equals k root h. Setting these equal, we get 4 pi dH/dt equals k root h. This is our separable differential equation. Let's separate the variables. We get 4 pi over root h dh equals k dt. We can write root h as h to the power of -1/2. Now we integrate both sides. The integral of 4 pi h to the -1/2 dh is 8 pi root h. The integral of k dt is kt. We add a constant c. We have two unknown constants, k and c. We can find them using the two conditions given in the problem. First, at t equals 0, h equals 9. Substituting these values, we find that c equals 24 pi. Next, at t equals 15, h equals 4. Substituting these values and our value for c, we find that k equals -8 pi over 15. The negative sign makes sense, as the water level is decreasing. Now we have our complete equation relating h and t. The equation is 8 pi root h equals negative 8 pi over 15t plus 24p. The final question is, how long will it take for the tank to empty? This happens when the depth h is 0. Setting h to 0, the left side becomes 0. We solve for t, finding that t equals 45, so the tank will empty in 45 minutes. This problem demonstrates how to combine related rates with separable differential equations to solve a complex application. The key steps were setting up the differential equation using the chain rule, separating variables, integrating, and using initial conditions to find the constants. Now that we've covered the theory and worked through several examples, it's time for you to practice. Here are 5 IB-style practice questions on separable differential equations. I encourage you to pause the video after each question is presented and try to solve it on your own before watching the solution. This is the best way to solidify your understanding. Question 1. Solve the differential equation dx equals y squared over x, given that y of 1 equals 1. Pause the video now and give it a try. Welcome back. Let's go through the solution. First, we separate the variables to get 1 over y squared d equals 1 over x dx. Integrating both sides gives negative 1 over y equals ln of the absolute value of x plus c. Using the initial condition y of 1 equals 1, we find that c equals negative 1. Substituting this back, we get negative 1 over y equals ln of x minus 1. Solving for y gives the particular solution y equals 1 over 1 minus ln of x. Question 2. The rate of decay of a radioactive substance is proportional to the amount of the substance present. If 100 grams of the substance decays to 80 grams in 5 years, find the half-life of the substance. Pause the video and try to solve this decay problem. Let's look at the solution. The differential equation is dt equals negative km. The solution is m of t equals m naught e to the power of negative kt. Using the initial condition m of 0 equals 100, we find m naught is 100. Using the second condition m of 5 equals 80, we find the decay constant k is 1/5 ln of 125. The half-life is ln of 2 divided by k, which is approximately 15.5 years. Question 3. Solve the differential equation dx equals x times the quantity y minus 1, given that y of 0 equals 2. Pause the video and work through this one. Here is the solution. Separating variables gives 1 over y minus 1d equals x dx. Integrating gives ln of the absolute value of y minus 1 equals 1/2 x squared plus c. Using y of 0 equals 2, we find c equals 0. Solving for y, we get y equals e to the power of 1/2 x squared plus 1. Question 4. A population of bacteria grows at a rate proportional to its size. If the population doubles every 3 hours, how long will it take for the population to triple? Pause the video and solve this growth problem. Let's see the solution. The model is p of t equals p naught e to the power of k to t. The doubling time of 3 hours means p of 3 equals 2 p naught. This allows us to find k equals 1/3 ln of 2. Now we want to find the time t when the population triples, so p of t equals 3 p naught. Solving for t, we find it will take approximately 4.75 hours. Question 5. Solve the differential equation ddx equals x times y squared plus y squared, given that y of 0 equals 1. This one requires a bit of algebra first. Pause the video and try it. Here is the final solution. First, factor out y squared on the right side to get dx equals y squared times the quantity x plus 1. Now it's clearly separable. Separating and integrating gives negative 1 over y equals 1/2 x squared plus x plus c. Using y of 0 equals 1, we find c equals negative 1. The particular solution is y equals 1 over 1 minus x minus 1/2 x squared. Well done for working through these problems. If you found them challenging, go back and review the examples. Practice is key to mastering this topic. Let's conclude by summarizing what we've learned today. We started by defining separable differential equations as those that can be written in the form dx equals f of x times g of y. We then learned the general method for solving them. Separate the variables, integrate both sides, and solve for y to find the general solution. We saw how to find a particular solution by using an initial condition to determine the constant of integration. Finally, we applied these techniques to model real-world phenomena like exponential growth and decay, and even a complex related rates problem involving a cylindrical tank. You are now equipped to identify, solve, and apply separable differential equations, which is a crucial skill for your IB Mathematics AAHL studies. Keep practicing and you'll master this topic. Thank you for watching.